Okay, here are the basics. We are combining current of electricity with DC circuits. So basically all the electrical stuff. What are the basics? We start off with current. What is current formula?
I equals to R over B.
You might want to start to revise with your notes and everything. What's the definition of current? These are all good 1-mark questions that will come out sooner or later in exams.
The amount of electrical charge flowing through a point in the circuit.
Rate of flow of electric charges. Because it's a rate, so you can apply calculus in this. I equals to dq over dt. Anything that has the word rate, you're differentiating with respect to time. So you have charge here, Q is a charge. So rate of flow would mean the change in the charge with respect to time. I is a current. What is the SI unit?
Ampere. A.
So this A. What's the SI unit of charge?
G. Coulomb.
So if the rate is constant, if you're talking about average, if you're talking about defining average current, then you can transfer it to this. Or some might say change in Q over change in T. Finding average. Just think about calculus. If you are finding, if I is constant, so let's have a space here. If I is constant, then you can bring the term over, integrate with respect to I. Basically, what you get here is area under current time graph. So in your syllabus, you're not expected to integrate. It's not maths, but you may be asked to find area under graph. Things like trapeziums, for example, the most common question you can come up with this, which we talked about it before as well. I, T, and they have two different values. Okay, you gotta find area under graph. So that's the thing about current. If you feel like none of this makes sense to you, you've forgotten about stuff, you should take this down. So there's like who's scared? There. Okay. Right, so this is just current alone, and there's a lot of stuff to deal with. Okay, so moving on, let's use the space here. We have potential difference. We also have EMF. Okay, so what is the definition of PD? PD definition. work done to drive a unit charge across a component, across an electrical component. Where electrical energy is converted to other forms of energy. So this is potential difference. This is based on example, if you have a resistor, okay, there's a potential difference here, right? And there's like charge going through the resistor. And because there's charge, there's work done. There's W. So if you put everything together, V equals to W over Q, work done per unit charge. So in short, if you want to memorize these things, work done per unit charge, work done per unit charge. Just got to keep repeating it. That's potential difference. So the energy, the work done, or the energy required actually is the electrical energy. And in the process, you have work done, electrical energy being converted to something else. In this case, for a resistor, the electrical energy is converted to what? For a resistor, you have electrical energy being converted to what?
E.
E. Okay, thermal energy. So EE is converted to TE. All right. Now there's also EMF. So I need space for EMF over here. What's the definition? Work done to drive a unit charge across the entire electric circuit where chemical potential energy, CPE, is converted to electrical energy. So basically EMF is at the battery. So EMF is actually at the battery or the power source. I need to move my head. Okay. At the battery or power source. So the battery is using chemical potential energy to convert to EE so it can drive the unit charge across the circuit. What's the difference between EMF and potential difference?
EMF is across the entire circuit, while potential difference is just across the electrical component.
Yeah, that is one thing, as what the definition says. EMF also depends only on battery. So if you have a 9-volt cell, if you have a 9-volt cell, it's still a 9-volt cell. No matter what circuit you put inside, it could be this. Okay, you could add on to another resistor. This 9-volt will still remain as 9-volt. A 9-volt cell will still remain as a 9-volt cell because this is the EMF. But potential difference can vary. Okay, so example here, right? This resistor is a 9 volt currently. If I remove this and I change to a 20 volt, then this one will also change to a 20 volt. So can you get a difference? The EMF depends on the battery. So whatever circuit you have is still a 9 volt battery, but the potential difference depends on the source. Okay, you connect a 20 volt battery, a 20 volt cell across it, you will get 20 volts. You connect 9 volt, you will get 9 volt. You connect 1 volt, you get 1 volt. Okay, so these are the essentials of the basics. Okay, we only covered, currently we only covered I and V. That's all. All right, there's more stuff. So why am I going through all this with you? A good way to help you remember things is to try to write it out. This is what we call a mind map. Now, obviously, my mind map is a little bit too big. Okay, yeah, you can actually put many things inside here. So I'm going to assume that I have a bigger mind map, and I'm going to erase all the ink. Have you copied this down?
Yeah.
Okay. So again, I'm just going to write this down, COE plus DC circuits. Assuming that you are continuing your mind map, you have covered V, we have covered I. What else do we need to cover?
Resistance.
Resistance. Okay. So what is resistance? Definition? It's a ratio of
The current and the charge.
potential difference across an electrical component to the current flowing through it. So you have R equals to V over I. But very importantly, you also have rho L over A. This one is more on values in a circuit. It's based on values in a circuit. This one is based on properties. Properties of the component. Rho L over A. The rho stands for resistivity, the L stands for length, the A stands for cross-section area. All of this has to be SI unit. So we have ohms here. Current is ampere. V is voltage. L is what? Meters. Meters square. Rho is then what? It's another thing. Rho is then ohm meter. Okay, essentials to resistance. The basics are. You can make your notes nicer, you know, decorate it a little bit if you want. Definition, a 1 mark question, put it here, then down here you can label it as formula. Right, so these are some ideas for you to help with making your own notes. Different colors if you want to, you know, highlight it with different colors, all the SI units, bring it out so it's not so monotonous. Okay?
Yeah, I don't usually do that, but okay.
Well, try something for a change.
Yeah.
Studying may not be very fun to you,
Yeah.
but it's really up to you to make it more fun.
Okay.
Yeah, so these are some solutions, some suggestions. Okay, so coming to what we were talking about just now, finally, terminal potential difference. So you have to know all the things in front. Okay, there's a reason why I went through all those stuff in front. And that's because it all leads down to this. It all leads to this because terminal potential difference has a formula. And what is it?
V equals to E minus IR.
Yeah. So everything we talk about, potential difference is here. E is what? This curly whirly E is what?
Internal resistance.
EMF of the battery. This is the terminal potential difference, the big V. EMF of the battery, which, as we mentioned, does not change. And this is the current in the circuit. And this is internal resistance. So as you write down this formula, you have to know how the circuit looks like. This is your small r, it's your I, it's your big R, and this is your E. So potential difference is VT actually. So there's a T here. Your VT is over here. Yeah. Okay. So sometimes you may be given a graph. How will you draw a VT versus I graph? Would actually look. So if you convert this using linear law, y equals to mx plus c. Your y is Vt. Your m is minus I. Minus r. If you are referring to a Vt versus I graph, your x is I and your c is your E. You get something like this. Negative gradient graph. Can you tell me what is the value of the x-intercept?
Huh?
What is the value of the x-intercept? If you have a Vt versus I graph, what is the value of the x-intercept? to find x-intercept, you have to sub y equals 0. So what is the value of the x-intercept? So sub vt equals to 0 inside. So why am I going through this review? Could be a question that comes out. They give you a graph and you're asked to find certain things from the graph. So you have to know what each of the values mean and the concept behind it. Where did we learn linear law from? What is this topic under? It's under your O-level A-maths. A-math. O-level A-math. Or H1 math. Okay, this covers that again. Right. So linear law is very much used in many of the physics concept that has graphs. You see graphs, you likely be looking at linear law. Okay. So there's actually a lot more things. There's maximum power theorem.
This is under what? Terminal potential difference still?
Yeah, internal resistance of a battery. So battery itself has not ideal. Ideal batteries do not have internal resistance, but some batteries or most batteries do actually have resistance in real life. So that's why you need to understand the meaning of terminal potential difference. Okay, this only if you're dealing with real batteries. The ideal ones do not have internal resistance. Maximum power theorem will thus state that for maximum power to be transferred, max power to transfer to load. The load in this case refers to this big R. The big R must equal to R. Yeah. You can actually get maximum power theorem. You can derive it by taking the total power equals to power through the internal resistor plus power consumed by the load. The big R is the load. Then you have IE equal to IR plus IV plus IV, or rather I squared R plus I squared R. Then because you have to, for maximum power, you have to differentiate power with respect to R and make it 0. So there's a lot of steps from there. I don't have space to write this in. But in your H1 syllabus, you're not dealing with much of that. So I'm just not going to talk about that for now. All right, but if you are doing H2, you have to learn more of this. Okay, so I'm going to just stop here for current of electricity. All right. Okay, so far?
Yeah.
Okay, so moving on to DC circuits. So we're still dealing with this mind map. Again, resistance. So you can have resistance in series, which is your R effective equal to R1 plus R2 dot dot dot. Okay, that is your total resistance in series. If you want to find the total resistance, that's the formula. It's not very straightforward. I'm not going to talk too much about it. Resistance in parallel. R effective is then equal to 1 over R1 plus 1 over R2 plus dot dot dot, inverse everything. Yeah. Okay. And of course, we have to bring in our good friend PDR, potential divider rule. Right? What does it say? If you have two resistors, two or more resistors in series, this is V1, this is V2, R1, R2, and the total is V. Then V1 is equals to R1 over R1 plus R2 plus dot 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 times V multiplied by V. So the potential divider rule is a very important rule because we'll be dealing with it in DC circuits. All right. So understanding how the relationship works is very important. For example, if I somehow were to increase R1 value, so put an increase here, can you tell me what happens to the V1? If I were to increase the R1 value, what happens to the V1?
Increase.
It will increase as well. Similarly, if I decrease it, then this will increase as well. So understanding this relationship is very important because you're not only dealing with ohmic conductors. So these are ohmic resistors, are ohmic conductors. Well, this is very cute resistor. Resistors are ohmic conductors, but you could be dealing with non-ohmic transducers, as they call it. So example would be LDR. And a thermistor. So these are non-ohmic conductors, which by the way, you have to know what's the meaning of an ohmic conductor and non-ohmic.
Yeah.
Yes, what is it? What is
like
it? Okay, so let's use the rating. An ohmic conductor follows what? It obeys what? As the name says, Ohm lah. So obeys Ohm's law. So what is Ohm's law? In mathematical sense, V is directly proportional to I, meaning PD across a component is directly proportional proportional to the current flowing through it. Wow, this is very nice memory. So if you're non-ohmic, means you do not obey Ohm's law.
Okay.
I will leave it up to you to fill in the properties of LDR and thermistor. I'm not going to give you everything. You have to walk through it on your own. Refer to your notes. Okay. PDR can also be branched out into other areas, like when you're using length. So potentiometers. Potentiometer is a device that changes in its length. So again, that is not, I've not seen that much in H1 questions. All right, H2 questions will come a lot, we'll have a lot of questions like that. So potentiometer, instead of dealing with R, you're dealing with length. So example of a formula will be something like this. You can change the length of a potentiometer. And the potentiometer will look something like this. It's a very long object. You have a crocodile tip. So this is the total length. And this is the L1. So you may have other length involved, okay, depending on the question. So this, if this is the only length that's involved, then you just put it under here. There won't be L1 plus L2 and all that. It will just be L2. Yeah. And that's basically all the stuff, the fundamentals, the concepts that we have for these two chapters. And the rest, all about applications, is about doing the questions again and again, which we are going to look through pretty soon. What you've created there is a cheat sheet. And you should hold on to that, bring that for every lesson. And then you wouldn't need to ask me, what is terminal potential difference again? Or I wouldn't need to ask you, but I will keep asking you to make sure you remember. All right, any questions? You bring that sheet home. You don't need to take a picture. Okay.